So today we're going to learn how to find area that's made up of multiple other pieces that we have to put together. Yesterday, we could do it all at once. We had a top function and we had a bottom function, and we could just find the area between them by doing top minus bottom. But today, we're going to look at two different scenarios. One scenario is that we have to split the area up if they give us two different functions horizontally. Like if I give you this, you would have to find the area under the red one first, and then you have to find the area of the blue one second, and then add them together. You can't do it as just one integral. You have to write it as two. All right. Another situation that we're going to look at later today, which also requires us to split it up, is sometimes you have two functions, and they don't cross at just 2 points, but instead they cross at 3 points. And when that happens, we also have to find the two different areas. So here we would just do top minus bottom to find that area. But then we would have to do top minus bottom for this one also and put them together. So we're looking at two different situations here today where we're going to be finding area like we were yesterday, but we have to do it twice because it's broken up into pieces. Okay, so that's our goal for today. Let's begin. All right, so the first one here is, it says, write but do not evaluate an integral expression that gives the area of the region bounded by the function y equals the square root of x and y equals 6 minus x. All right, so I would say that this function here is the curving one. And I would say that this function here is the linear one. And this is one of those situations where I would need to split this up into two pieces. I would need to find the area on the left, which is only doing one of the functions, the red one. And then I would need to find the area on the right using the other one. Okay, and then we would add them together. So we have the area of the red function, and then we're going to have the area of the green function there, and then we're going to add those together. Now, I think where most of the work lies here is in finding the limits. Okay, so for the red one, it's kind of obvious we're using that function there, and for the green one, we're using the 6 minus x, right? But like I said, what makes this challenging is figuring out where do you start and stop for each one. Where does the red area start at? 0, yeah. So that one's cool. But it stops right here at this intersection point. We learned how to find those yesterday. So we need to find that. But that's where that one's going to stop. Then we need to do this one. The green one is going to start where that last one left off, and then it's going to stop right here, which I also don't know that point, so I also need to find that, and that'll be a new thing for us a little bit today to find as well. So to get this thing completely done, I basically need to find those intersection points to get the answer. Notice the directions are saying write but don't evaluate. That means I don't need to figure it out. I just need to write the integral, and that's all we're going to do. So let's find the intersection points. How do you find where they intersect? Well, we did that yesterday. You set the functions equal to each other. So I'll label that intersect. And we're going to have the square root of x is equal to 6 minus x. Let me ask you guys your thoughts here. If I want to solve for x, Kahindi, what would you do first if you want to solve for x? Square both sides. So these go away, and this is 6 minus x times 6 minus x. So you're going to have to FOIL that or do the box method. I'm going to let you guys do that for algebra practice. So go ahead and take a minute and find out what is 6 minus x times 6 minus x, and I'll ask you what you got. So we get that if we FOIL it out. Elias, what do I do now? It's a quadratic. So we have to do something kind of weird when we have quadratic. What do I do first? Move the x. Yeah, when you have a quadratic, you need it to equal 0. It's not something that our intuition tends to go towards, but that is what we want to do. Move it, so you want to equal 0. Let's go and take a look at the next one there. Nelson, what would I do now? Okay. Let me try one more person, and if they don't know, I'll tell you. Ty, what would you say we do now? We're going to factor. So we're going to break this apart like this. And once again, I'm going to let you guys do it because I want you guys to practice this stuff. Okay, so now we set them both equal to 0 and we solve. So I get x equals 4 and I get x equals 9. Now that's a little bit of a problem because I have one intersection point, but for some reason I got two different answers. Now, I'm not going to go into why there's two different answers, but I will say that one of those is this point right here, okay? This is either a 4 or it's a 9, and we're going to have to figure out which it is. How we're going to know which it is because we're going to find this point, and hopefully it's a number that, you know, will tell us kind of which one it has to be. All right, so that's that. So we have to find where they intersect, and we just accomplished that feat, setting them equal. Now the next part is a little bit new, but some of you guys might have an idea of how to do it. Let me clean up here. The next thing I want to do is I want to find out where that green line is touching the x-axis. Any thoughts on how to do that? How can I tell where this green line touches the x-axis, or intersects, I guess we could say? Any thoughts? Set it equal to 0. Yeah, because the y value of the x-axis is 0, right? And the y value of our green function is this. So you set them equal to each other. So you do 6 minus x equals 0. And if you add x on both sides, it turns out x is 6. Now we know. If this is 6, what does this point have to be, 4 or 9? It's got to be 4. It can't be 9, right? So we'll go ahead and cross off the 9. It's got to be 4. So now we know our intersection points, and we're good to go. So the red region goes from 0 to 4, and the green region goes from 4 to 6. And we're done. We're not going to do any more than that. Even though we could, we're not going to. So we had to find the area of each of these things and put them together like that. Now we are going to learn a strategy later on where we can do this all with one integral, but that's for after spring break. But for now, we'll think of it as two separate integrals. All right, so you got to find the place where they cross, and you got to find the place where they touch the x-axis if you want to be able to set it up right. So if you want to find where they cross, you set the functions equal. If you want to find where it touches the x-axis, you set it equal to 0, right? So we're going to do this one now. We have two parabolas. One's red and one's blue. And I want to find the area between those two parabolas and the x-axis. So here's the x-axis, and the area between them would be like that little triangular region there, so I'll shade it in. We want to find this area right here. Now, to do that, though, we're going to split this up into two areas. The first one on the left, that's for the blue function. The one on the right is the area under the red function. And we have these three mystery intersection points that we need to find. All right, so I'm going to let you guys do that, set it up, and we'll see how you... So we want to find B. That's where the two functions are intersecting. Diley, how do I find where the two functions intersect? What would I have to do? You equal them both to each other. Good. We also need to find A and B. I'm sorry, A and C. Those are x-intercepts. That's where it's touching the x-axis. So, Eric, how do I find the x-intercepts? That's right. You set the equation equal to 0. So for A, that's the blue one, I'm going to set the blue function equal to 0. And for C, I'm going to set the red function equal to 0. And I'm not sure where you guys are at, if you've got how far you've gotten so far. So let's just see what you have. Jacob, did you get point B yet? It is 3. Nice job. Elena, did you get A? I agree. And last one, Jazir, did you get C? Okay. Vega, did you get C? What'd you get? Yeah. All right. So this is 1, 3, and 5. So we can set up our integrals now. We're going to have two areas, right? The first one goes from 1 to 3. The second one goes from 3 to 5. For the first one, that's the blue line. For the second one, it's the red line. And that would give us the area between those two functions. Okay. All right. Let's move on to another situation. All right, so consider this graph here. We have two area pieces here, right? The first area piece goes from A to B. The second area piece goes from B to C. Now, this is more like what we learned yesterday, where if you want to find the area between the blue line and the red line, you just do top minus bottom. So if I want to do the area of the piece on the left, that would be the integral of the area from A to B. And the function that comes first is the one that's on top is the blue line. That's f of x. So for that one, I would do f of x minus g of x. For the second integral, that one goes from B to C. And that one's reversed. On that one, the red function is above the blue one. And so that one's going to be g minus f. So we have to be able to discern which one is on top. So when functions cross more than once, you're going to have multiple areas set up. And every time you go from one to the other, the order is going to switch. Because every time they cross, they switch places. Okay? All right. So that's how you can find area of two functions whenever they're split up into different pieces like that. All right. So let's take a look at an example there. This is review. We talked about this yesterday. How can you remember which one's on top, which one's on bottom? We talked about that yesterday. You just pick a number and plug it in. And we're going to get to do that again here. All right. Write but do not evaluate an integral expression that gives the area enclosed by these two functions. All right. So step one is to find the intersection points. How do we do that? By setting them equal to each other. Then we get it to equal 0, right? So I'm going to move everything on the left side out of the way. So these are all gone. This is 0. This is 8x. This is gone. And that's 2x cubed. All right, let's go ahead and move on. So the next step we got to do is factor it. So, okay, Hinde, what can I take out here? What can I factor out? And 2x. So that'll give me 4 minus x squared. Okay. But we can factor more. You guys, I don't know if you recognize this. We don't see them a whole lot, but they're nice when you do see them. That's a difference of squares, right? So you take the square root of that, and that, you make one a plus and one a minus. All right? Difference of squares. And then you set all three of those equal to 0 and solve. This one I get x equals 0. This one I get x equals 2. This one I get x equals negative 2. So that means these graphs are intersecting 3 times. Now I don't know what these functions look like, okay? But just to give you a fudged picture, a make-up idea of what it is, I know that they're intersecting at negative 2, at positive 2, and at 0. So I'm just going to put 3 dots here really quick. And basically I have 2 lines. I've got one function, and then I've got another function, and they're crossing at those 3 values. And so I have these little areas that I need to find. And we're going to have 2 integrals, right? The first one's going to go from negative 2 to 0. The next one's going to go from 0 to 2. And for each one of those, we need to decide which function is the one on top, and we talked about how to do that yesterday. Okay? Now, if you were to try to graph those functions, I'm pretty sure it wouldn't look like what I drew, but it doesn't have to. It still communicates the same idea, and that's all that matters. All right, so my first function is going to be from negative 2 to 0. The other area or integral is going to be from 0 to 2. Now, I don't know what it is right now. I don't know if it's f minus g or if it's g minus f. So we're going to pick a number and plug it into f and g. So for the first one, let me ask somebody here. Magdalene, what would be a good number to plug in here to test? Any number between your upper and lower, right? So negative 1's a natural choice there. Let's plug it in. If I plug negative 1 into the f function, I get negative 3. If I plug negative 1 into the g function, let me do a little mental math here. Negative 12, negative 9. So in that case, this one's bigger. The f is bigger. Therefore, f comes first. And it's pretty rare that they wouldn't just reverse in the next one, so I think it's okay just to assume it's going to do that. So the next one, they're going to be flipped. It's g minus f. I mean, to be safe, you can still check it. The only reason why it wouldn't is like when they intersect, instead of crossing, they bounce off of each other. That's possible, in which case they wouldn't switch places, but that's pretty rare. I think we could assume it's just going to be like that. And that's where we'll stop. So there's that one. So you wouldn't know that it's this kind of a problem at first, but when you solve the intersection points, you get 3, and you think, oh, aha, this is one that requires 2 integrals. So you have to do it that way. All right? If you only get 2 intersection points, then it's like what we did last time. But when you get 3, you got to do it that way. Now, I'm going to ask you guys to make a change on here. I would like you guys to change this one to be y equals 7x minus x cubed. And I'd like you to change this one to be y equals negative 2x. Okay? So go ahead and work that one. Okay, so we start by finding those intersection points, setting them equal. adding that 2x over. Taking out an x. I'm going to go with a difference of squares approach there. This one gives me x equals 0, this one gives me x equals 3, and this one gives me x equals -3. So I've got two functions crossing 3 times, which means we have two separate areas. So I'm going to be setting up my integral. You start with the lowest, then you go to the next one up, starting from there, ending on the highest one up. And we have to figure out which one goes on top. Now, a lot of you guys wanted to put f and g in here. If it's a multiple choice, it doesn't matter at all. If you're doing an FRQ, if you're going to create new letters like that, then you have to define it that way somewhere at the top of your paper. So if you want to say, okay, this one's the f function, and this one's the g function, you can do that. Or, instead of using f and g, you could just put the functions in exactly as they appear. Either way, but you can't just, it would be bad to just put f and g here and not define them on an FRQ. You have to say what f and g are. So, for the first one, I'll go with the f and g notation. No, I guess I won't. I don't want to confuse them. We have the 7x minus x cubed and the 2x, right? I'll pick a number between -3 and 0. We'll go with -1. And then the other one is -2 times -1. And we'll see which one of these comes out greater. This is -7 plus 1, which is -6. This one's 2. 2 is bigger, so the -2x is bigger. So you would do this one first, followed by this one second. For the first one, and on the second one, it's safe to assume they probably just reverse. So it looks like that. Notice the directions say write but do not evaluate. So even in your homework, if I say write but don't evaluate, you could stop here. You don't have to go any further. But if I say evaluate or find the area, you do need to keep going, just to be aware, okay? All right, last topic for the day is, I think you'll appreciate this, a little bit easier. Before I go into it, I'm going to remind you of something. You don't need to write this, but you guys may recall we talked about a rule about integrals that looked like this a while ago. See if you can remember what that was. Ariane, do you remember what these would be here and here? So we learned a rule a little while back that so long as these things are the same, if this one goes from A to B, and this one picks up at B and goes to C, you could pretty much just put this together as one integral where you start at A and end at C. Okay? So we talked about that little rule. We're going to use that to our benefit here. Now, why do we do top minus bottom? Okay, well, because that keeps the area positive, right? So for the first half over there, we have f minus g, right? But that's positive, correct? So don't you agree that that would be the same thing as this? It's positive, so if you take the absolute value, it doesn't change it, right? The other one over here is g minus f. Well, I had to reverse it. That way it's top minus bottom, so it ends up positive. So don't you guys agree that would be the same thing as this? Right? Now I want to show you something interesting about those two things. These two things are not the same. F minus g is not the same as g minus f. But what's 2 minus 5? -3. What's 5 minus 2? If I do this, what do you notice about those two things? They're the same. So f minus g, which is f minus g, and the absolute value of g minus f, which is the same as g minus f, those two things are actually equal if I put absolute value bars on there. Which means, remember how we had this little thing before? Right? Well, since I'm allowed to do that, still positive, and that, still positive. But by doing that, these now become the same, which means that we can put these together in one integral. It doesn't matter which one you used because they're the same. And we're going to start at A, and we're going to end at C. Okay, so here's what I want you guys to write on this slide. If you have a calculator, it works really well for calculator problems. All you really care about is the first point and the last point, A and C. You don't even really need to worry about which one's on top. If you just put absolute value bars, it won't matter. And we could just do that in our calculator and be done with it. We don't have to split it up into two pieces. We don't have to figure out which one's on top. If we have a calculator, we can just punch all that in like that and have our answer pretty quickly. Okay? If you have to do it by hand, then you have to do what we did last time. But with a calculator, we're going to do that. And we're going to actually do stuff like this quite a bit in here. So it's a good little strategy to be aware of. So let's go ahead and do our first one here. Get a calculator, and let's graph these two functions. But before you do, remember, my pre-calculus students are sharing our calculators. So every time you pick up a calculator, you need to reset it. Second plus 712. All right, guys, so it should look something like this. We don't really care about any part of the graph except for the area between the curves, which would be like this little thing here. And then I'll use a different color for this one over here. So we have these two little areas. Now, we don't need to find the area of the brown one first and the area of the orange one second. We could do all this at once since we're using a calculator. All I need to do is I need to find out where they intersect first and last. That's what's going to go here and here. And then after that, I'm just going to put the absolute value of the difference of those two functions. And I'll be able to get the whole thing, the brown plus the orange area combined. So let's find those intersection points. Do second, oh, he's not here today, but sorry. He's not. Sorry. Do second, calc, and intersect. Magdalene, she was trying to hold it back. So 1 and 5. And now we're just going to do it all at once. You need to have your absolute value bars on there, and you do your y2 and y1. Once again, now if this was an FRQ, you would not want to write this on your paper because in the directions I haven't called any of these y2 and y1. So I would have to take the time to do this, or I would have to just take the time to actually write the functions out. So don't just make up letters, remember, that's not good in FRQs. But I've defined it by drawing little arrows, so I'm safe now. But go ahead and do that. If you guys forgot where the absolute value button is, you're going to push Math. You're going to scroll over to the right one time, and then you should see it as option number 1, absolute value, ABS. And you should be able to get an answer there. So if you have a graphing calculator, you don't have to split it up. You could just do one integral, but don't forget those absolute value bars, and that'll work. All right, so last one is for you. I'll let you guys do that from beginning to end on your own. I do feel a little